Good afternoon, everyone. I'm Rajsekar Manokaran. I'm an assistant professor at IIT Madras. I'm here to talk about average case analysis of restricted Boltzmannian machines. Restricted Boltzmannian machines are simple machine learning models that I will be talking about, but I want to get a sense of the audience. So I'll just ask, I just need to know what is the expertise level on machine learning and complexity theory. So a quick show of hands, who is comfortable with machine learning jargon, like just simple things like clustering and supervised learning and things like this. Okay, and who is comfortable? Who are all comfortable with complexity theory notions like NP hardness and things like this? Okay, sounds good. So it looks like the basic complexity is pretty well known to everyone. I'll just explain the machine learning models. So I'm going to be talking about RBMs, and this is based on joint work with my student Aditi Raghunathan. So let's see what an RBM is, or in general what it means to be doing machine learning, right? So in general in machine learning we have a bunch of data, and then we are trying to make some prediction. So mathematically it's really just a function taking data and then outputting some useful information. But the twist in machine learning is to use what is called a model. So what we have is again just this black box function that we are trying to define, and then we give it data and then try to understand what it outputs. Except here now this function is going to be parameterized by a bunch of parameters, and these are the parameters that the machine learning algorithm is going to learn. So what we do is we take the data, and then depending on the problem we kind of come up with a model. This can either be some well-known model that's already there in the ML community or something new that we come up with. And then we take a bunch of data that we already know the answers to, and then try to figure out what this theta should be. And once we figure out this theta, we apply it in practice and then give it new data and then use the value here. So this is basically the setting that's used in machine learning. And instead of talking about it in the most general setting, I'll talk about RBM. And the main reason RBMs were famous is for their really good performance in the Netflix challenge. So the Netflix challenge was something that was announced by Netflix.com. And they had their own machine learning models that could predict a user's rating for a movie where the user hasn't rated. And then they weren't very happy with it and they wanted to improve it. And they had asked the community to give them models that could predict better. And this RBM came up in that setting. So I'll describe it in the setting of the Netflix challenge so that it's easier to understand. I should note that the goal of the talk is not to describe RBM and all the math behind it, but really to expose a bunch of open problems in machine learning, which might be interesting, or suggest a bunch of mathematical techniques or complexity theory techniques that will be applicable to other fields represented here. Okay, so feel free to stop me and ask me any questions if you have. So in the Netflix challenge, posed as a machine learning question, we are given a bunch of movies, and the users, any particular user's ratings of the movies. And for simplicity, we are going to assume it's 0 or 1. So either the user liked it or didn't like it, instead of 1, 2, 3, 4, 5, which is actually what was the Netflix challenge about. Okay, the extension is actually simple from 0, 1 to any other domain. And so the model that the RBM describes is like this. So in the setting of movies, we're going to write down movies on one side, and then there's going to be some hidden part. I'll describe what the hidden part is. So now the movies are listed, and then we're just going to really create a graph based using movies and some hidden nodes. So the idea is that now we have a bunch of movies, and we are trying to use some of the ratings that the user has given for the movies to figure out the ratings for the rest of them. So somehow we want to capture the information that the user has in the hidden side, which is not actually shown to the end user. So really the model is just some kind of a weighted bipartite graph. I'll call this A. And given values here, 0, 1, and suppose I also have values here, which are again in 0, 1. What the RBM does is it assigns some probability to a specific bunch of values here and a specific bunch of values here. Now this will explain why we call it RBM. So the probability of, yes? So on the left hand side, the nodes represent a fixed, the ratings for a fixed movie. So this node would be a rating for a fixed movie. I'm not talking about the user yet. That will be clear when I fully describe the model.
So there's one movie, and first is the rating of one user.
No, there are a lot of movies. Once I describe the distribution, it will be clear where the user comes in.
Okay. So each node is a different movie?
Yeah, each node is a different movie. It's a list of movies.
Okay. And on the right side?
On the right side is my information of, it's something that's actually hidden, and the right side is what the model is storing about the user. So it will be clear once I just describe this distribution.
So each node represents the user?
No, there's no name for it. It's just internal representation.
Latent variable.
Yeah, so the general idea in machine learning is to somehow, or at least in these kind of models, is to somehow emulate biological processes, and in particular, emulate the brain. So a simple idea is to, I mean, it's not good to go into that detail. I'll just describe the distribution. I think the overall problem will be clear. So given a bunch of values here, and let me call them some v belonging to 0, 1 power m, and given a bunch of values here also, let's call them 0, 1 power some n, the probability of this v comma h is defined to be proportional to e to the power v transpose ah. So the idea is that the model tries to act like each of this edge somehow encodes some interaction between the endpoints of the edge, and then it uses a simple Boltzmann style distribution to obtain an overall distribution over the system. So given this, what this means is that the RBM is really given the matrix A, is just a distribution over v comma h belonging to 0, 1 power m plus n. Okay, so once we are given the weights, it's actually given the matrix A, it is actually just a distribution. And the use case, for instance, the use as by this was as used by Hinton, Ni, and Salakuditno, and this is from 10, I think ICML 10 or 9. So the use here is that we already have a lot of user data, and what we do is for each user we feed it in, and then somehow train the system to obtain an A. And now when we are given a fixed user, assume that we already have A. I'll come to how the A is obtained. Assume we already have an A, and now we are trying to find the rating of a fixed user on a movie that he has not rated. Then what we do is we simply assign all the values that are already known. So we have the ratings of some movies, we assign that, and the rest of them are just initialized randomly. The use, we can, for each user we have a bunch of ratings, we just feed it to the left hand side, and that's about it. For the same user, we can use this model and figure out what he might have rated other movies as. So once I describe that, that'll be clear. So the usage idea is, so we are given a user and some ratings. So the input is the user and some of the ratings. And we also have a pre-learned model A. Right? Here the model is being represented by one weighted matrix, and that's already learned, and we assume that's input. And the output is to, let's say we also have another movie M naught, where we want to find the rating, and let's say this is M naught. So what we are going to do is first initialize the left hand side as we would expect. So whatever movies we know, we are going to assign that value, and whatever we don't know, we are just going to assign random values. Okay, and then now what we do is we sample H given this particular V from the distribution of A, distribution induced by A. Okay, is it clear what this means? So recall that when I fix A, this is going to be a fixed distribution, and now once I fix the V, H given V is also a fixed distribution, and all I'm doing is I'm really sampling H0. So I'm sampling H from V, and then now sample the particular rating V0 given this H, again from the same distribution. Okay? Yeah, V0 is the rating for M0. And this gives me some probabilistic answer to what the rating would be. If we want expected value, we could just sample it a few times. Yes? So the reason, the hope is that when we sample H from V, we are transferring information about the user to the hidden side, and then now we are getting back the rating at a point where we don't know. And the hope is that the overall model A encapsulates all the information about all the users in the system. Well, they won the Netflix challenge in like something like for about 3 months they were the leader in it, so they got some prize.
No, I'm saying like example, we not already knew M naught.
We didn't know M naught initially. So the movie M naught is something where we don't know the rating. So we just initialize things we know, and then we leave it out, or we just fill it randomly, and then now we propagate it to this side and then come back, we get the value for the movie that we didn't know. Now we could also have done this with a movie where the rating is already known. That's where the hope comes in. The hope is that this thing is biased enough that it doesn't change the answer too much for things where the user is already very biased. We'll talk about this in the rest of the talk, where we'll try to explain theoretical ideas that we can use to talk about this system. But this is the overall picture. The only thing I've left out is how to learn A. So how do we learn A? So this again is a pretty standard idea in statistical learning. We have a model, and then we have, let's say we have some training data. So training data here just corresponds to collection of V1 till some Vt. Each of them belongs to 0, 1 power m. So we just have complete information from some users, or we just have a bunch of complete information, and that's going to be the training sample. Okay? And I will not describe the complete algorithm to train, but it's going to just use maximum likelihood training or maximum likelihood estimation. What does that mean? We have a bunch of parameters that we want to understand. So what we do is, given these V1 to Vt, which of these thetas is the most likely theta? That's the question we ask. and we'll assume that V1 to Vt are independent samples from the distribution. So what we're asking is the maximum over theta or minimum over theta, depending on whether we want to maximize or minimize the energy. The probability of seeing samples V1 to Vt. Okay, so this is a standard concept in statistical learning, and in the setting of RBM, there is a bunch of tedious calculations that we don't want to see, but this essentially amounts to being able to sample from the distribution. Okay, so the fundamental piece that's needed in training these RBMs is the ability to sample given a particular matrix A. Okay, and now we'll talk about the first theoretical insight. This is actually a work of Long and Servideo from 2010, where they used insights from complexity theory and approximation algorithms to prove that this model is actually extremely hard to optimize. Okay, so I'll give a quick proof of this result. The main theorem is that in general, it is hard to sample from any distribution that's even epsilon close to A. Okay, so in general, it's not only hard to get the exact distribution, but anything even close to that. Yes?
I did not understand something on the previous section. So you are assuming that these are independent, the V1, V2, Vts are?
Yeah.
In your MLE calculation, right?
In the MLE calculation, I'll assume these are independent.
But if the same user is rating all the movies, then why they have?
If the same user is rating all the movies, no, it's the model that's changing, right? The data is fixed. I'm going to assume that there is one RBM that is able to generate all this V with some particular hidden setup. So now I'm going to just guess what the size of the hidden number of nodes should be.
Okay.
And
So coming back to the question here, suppose I have one user who is rating two movies versus two separate users who is rating the two movies.
Yeah.
Okay. How does the model differentiate between these two situations?
Well, it depends on the assumption. I think the assumption of those authors was that the RBM encapsulates the overall data of all the users and doesn't really care if it's the same user or not. Because in the way it's used at the end, it's one single user and you're trying to find the rating of a single movie. And so you just initialize it with the values of that user, propagate and get back a value for a movie that's not been rated yet. So the hope is that the model fully encapsulates all the user data. Like this result says, it's actually, the model is not exactly optimizable in for every possible instance. So it's not clear that this model is theoretically useful. I mean, it's probably, given this result, it's probably not going to be possible to come up with algorithms that can solve this in general. But then again, we have insights from approximation algorithms that let us solve these kind of models when the weights are somewhat random. Okay? Yes?
I just want to make sure I understand. So V is a feature vector corresponding to, each movie has a vector V.
Each movie
Of features, right? And each user has a vector H. And then if I have A and I have V and I have H, I can predict the likely rating of that user for that movie.
I think the intuition is that H is the number of the features. So the V part is actually just the ratings of a fixed user. So VI is going to be the rating of movie I by some fixed user. And when I train, I'll just use data from all users and train it. And now the hope is that the weights will somehow encode the behavior of all the users together.
What is the dimensionality of this? So there are n different movies and n different users?
So this is under the control. Yeah.
But don't movies also have features? Or we think of each movie as its own feature?
So for instance, this could just become, we don't want to fix what each feature is. So, so the thing is, the history is that the existing algorithms in that Netflix was using used a lot of feature engineering, which means that they were solving clustering algorithms.
Each movie you are not categorizing in terms of features or
but the user.
No, it might end up happening. So it's very possible that this one node corresponds to action movies. And then this corresponds to comedy or something. Yeah, we don't care to say it initially. So we just say, I'll give you 1,000 hidden nodes and just optimize. Yes?
So n is the number of movies.
Yeah.
And n is the number of features that we use to classify users.
N is the number of features, full stop. N is the number of features to solve this problem. We are not going to think about what these features are, because that will mean that we are essentially feature engineering.
Yeah, I understand. So sampling, what you say sampling from A means sampling from pairs V comma H.
Yeah.
And the pair V comma H, V is a movie, and
V is a bunch of rating, V is a rating vector.
V is a bunch of ratings, and A is a feature vector for H is a feature vector for each. So sampling from A means producing sort of random-looking users, where here are their feature vectors, and here are the ratings they give off.
Indeed, yeah. So, so this model, maybe it looks very artificial, but then there's like a special case of what are called probabilistic graph models, where we just have a bunch of vertices that encode data or output nodes, and then we have edges that represent interactions between these nodes. So whenever we have an edge between this and this, we want to say that somehow the value here and the value here are related. That's, yes?
necessary that all your VIs should be having the same dimensionality. All users, your training data.
Yeah, because we want to feed it into this, and then we somehow think of each node as corresponding to one particular movie.
So all those training data should consist of all users who have rated all the movies.
If it is,
They're all 0, 1 to the n. I mean, they can't be subsets of 0, 1 to the n.
yeah, if we don't have information, one thing you can do is just insert random numbers there.
It would be a partial information. Not all
Right.
users may have rated that.
Right. So let's say we have answer here. So 1, 0, 1, and then we don't have answer here. We could just initialize it with a random number 0 or 1.
When you look at this data, training data, right?
Yeah.
V1, can V1 say rate movies 1, 3, 5, 7, and so on? V2 could have rated 2, 4, 6. Put the data.
Possible, but for the model, I'm going to assume all the data is there. The training sample is a bunch of fully rated vectors. If you only have partial things, well, you only have partial things. One way to circumvent that problem is just to insert random values for the other things.
Do the same.
Exactly. Yeah, do the same thing that's happened here. But that's one way. There's no proof that that's the only way to work with it. And also in the general challenge, what they did was to replace each of these with 5 nodes. And the 5 nodes, one of them would be 1, corresponding to what rating the user gave. That's how they used it for the general Netflix challenge. Yeah, so I will talk about this. Let's talk about this theorem. So what we are saying here is that this comes from some simple ideas in approximation algorithms. And what we are saying is that in general, this model is pretty powerful. It actually can't be sampled from. So I could give you a matrix A where, or you could never give me an algorithm where I can input A to that algorithm and then it outputs a sample. Was that clear? So in general, the problem of sampling from this distribution is very hard, is NP hard.
You're explicitly given a.
Yeah. The reason we want to look at that problem is that if we in general want to figure out the parameters, the best parameters, as it turns out, this expression, when we find the gradient, it just corresponds to sampling from this distribution. So it's not a very hard calculation to do. We just need to write it down. And as someone pointed out, this expression becomes a product of probabilities because V1 to Vt are independent. And we just need to like take logs and take derivatives and things. So at the end of the day, the thing is that if we could sample from the distribution, then we can also figure out the gradient at any point. So theta is actually just A. Yeah, A is equal to theta. Yeah.
These two steps in the output are
Easy, yeah. So in fact, when I spoke about probabilistic, I wanted to not talk about it, but in general, we didn't need a bipartite graph here. We could have a very generic graph where things like this are also connected. As it turns out, these two steps will become very hard. These two steps, when it's bipartite, is easy because the V is fixed and then it just becomes a simple bunch of, becomes a product distribution which you can sample from. So that's one advantage of these kind of bipartite graphs, and that's why this model is called restricted Boltzmann machine as opposed to just Boltzmann machines. N is just a function of your computational power, really. If you could increase N, you would be training better, and it's going to take more time. So N is more or less like a computational bandwidth. So maybe I'll finish up this proof. Really the main idea is that when we are looking at V transpose AH, and then we are trying to minimize over V comma H belonging to 0, 1 power some things. This is well studied in mathematics, and it's called the Grothendieck's problem. So the first step is that we identify that minimizing V transpose AH given V comma H belonging to 0, 1 power N, N or M. This is called the Grothendieck's problem. And what is known is that this is APX hard. So APX hardness is just a notion similar to NP hardness, where we not only say that finding the exact value of this minimum is hard, but we also say that even finding any good approximation to this value is hard, right? So APX hardness just says that finding even a 1.001 approximation is hard. Okay? And the rest of the proof is actually conceptually very simple. Since the energy term is in the exponent, really the distribution is very focused towards terms which have very low energy, right? Because it's e to the power that, and e to the power minus is just a strictly decreasing function. So anything with high V transpose AH is going to have very low energy. So really when you're trying to minimize and figure out what are the VH, or when we're trying to sample this distribution, it's going to be concentrated around points which have low energy, right? So all we have to do is prove that samples have low energy and in fact close to optimal energy. Where by optimal energy, I'm talking about the minimum value here. So given a particular A, there is some particular minimum value, and what we are claiming is that in general, it might as well be the case that these samples have energy very close to that minimum value. And why is that? That just comes from simply scaling the values of A, right? So as we increase the multiply all the values of A by the same constant C, the distribution is just going to get more and more skewed towards the optimal value. So once we play with the parameters, we can show that even if you could sample from a distribution that's somewhat close to the actual distribution, we would end up getting a point that has energy very close to this optimum. And since this is APX hard, we know that in general sampling from the distribution of an RBM is very hard. Okay? And okay, so this is one of the insights I wanted to talk about. The other one is just somewhat of a dual of this. So again, in approximation algorithms or in complexity, what we do is once we know that some problem is very hard to answer, we try to do average case analysis of that, which means that we just try to at least prove that this will work when A is random, or in some sense something is not the worst case. So the simplest thing we could look at is if A is completely random, and then let's say we want to figure out figure out an algorithm that can sample from the distribution. So that's the last component I wanted to speak about. So interestingly, here we can use some ideas from random matrix theory and an algorithm that came up in the approximation algorithms field to actually sample when A is quite random. So again, I'll just talk about the intuition. So now let's assume that A is random. What does that mean? It just means that Aij is independently chosen from some distribution. So maybe it's easier to assume it's just uniform in -1, 1. But most of these results apply for any fixed distribution with bounded variance and things like this. So when A is random, what we can show using random matrix theory is that if you plot the eigenvalues of A, then the number of eigenvalues number of eigenvectors whose value falls in a particular range like this is just the area under this particular curve. And this has a specific name. This is called the semicircle law. So the curve, the parameters of the curve are some equations. So given, let's say I have A, and then let's say I scale it in some special way, then this curve is just going to be the unit circle, x squared plus y squared equal to 1. Okay? And the key point here is now that since A is random, what we can show is that this part of the graph, for a reasonable notion of random, this part of the graph contains only little o of n eigenvalues. Okay? So in this part, I'm kind of assuming A is square. So it's an n cross n matrix. Much of this holds even if it is rectangular, but then I would have to use what is called a circle law instead of semicircular law. Because for rectangular matrices, the eigenvalues could be complex numbers. So I'll assume that A is a square symmetric matrix, and each entry is being picked independently at random in the upper half. And the lower half just gets copied to make it symmetric. Okay? So in this if we assume that A is according to this distribution, then it turns out that the number of eigenvalues that fall in the number of eigenvalues that have high value is pretty small. In particular, it's some number that goes to infinity slower than n. So what this means is that now we can use a technique from So there's a technique of eigenvalue and eigenspace enumeration. Which was popularized by a pretty important work of Arora, Barak, and Steurer from 2009. This again came in the setting of approximation algorithms where they wanted to solve what's called the unique games. And the idea there was again to somehow bound that the interesting bunch of eigenvalues is small. And then what we do is just take these vectors, make an epsilon net within the space, space spanned by those vectors, and just brute force search using that epsilon net. And the point now is that since the dimension is small, the size of the epsilon net is also small. So it's going to give you some algorithm that runs faster than a naive brute force 2 to the n algorithm. So this kind of eigenspace enumeration seems very powerful, in particular in attacking random instances of machine learning models. So it seems like there are a lot of different models that we could try to attack using this eigenspace enumeration method. And in particular for RBMs, we are able to show that for specific random distributions of A, we can in fact get a sub-exponential time algorithm that can figure out the distribution, that can sample from the distribution. Any questions? Yes?
This first question, so when you say JTX hard, you're saying if I get a randomized algorithm, for example, then that would violate, that actually will find the point very close to the solution, so that violates JTX hard.
Yeah.
Normally when we say JTX hard, we assume it's JTX hard for polynomial type of algorithm, but this is for like randomized algorithm.
Yeah, indeed. So I have to assume it's NP hard for randomized algorithms to give a good approximation. That's correct.
And this is what, when you say that you are able to solve this for random matrices, it's like probability close to 1. You will solve like if I randomly sample a matrix and give it to you, then
With probability close to 1, I'll solve it in time 2 to the n to the something, 2 to the little of n.
But some matrices I'll give you, if I randomly, you won't do it.
Yeah, that is proven here. There are matrices which, no, I mean.
From the sampling even from that, I
Well, it's up to a scaling. So up to a scaling, it covers every matrix. Yes, Deeparnab?
Yeah, so they did not use any algorithms of this.
So Netflix people used some heuristics which are extremely fast. I can tell you a little bit about it. So just like how you pointed out, the general distribution is hard to sample from, but if you fix any side, you can sample the other side. So what they did is some kind of Markov chain walk. So they just start from a fixed V and then go to some H and then go back to V and so on. And by the other result, we know that this is not going to actually converge. But then in practice, they even just do one step of this random walk and optimize. That's what the Netflix, these people did, and that already gave them very good results. So I mean, that part is not very well understood why it works. Because using this, we can show that there are matrices which where the random walk should take too long to converge. But then for all practical inputs, it seems to converge much faster. No, for random matrices, I don't know. I can't figure now. You had some question?
I guess you just answered one of my questions. So in some recommendation systems, the movies and users are treated in a similar way on either side, or sort of a dual way, so that movies have attributes which we're trying to learn, users have attributes which we're trying to learn, and then, once we have some training data, then a new user will look for users similar to that user.
Yeah.
And if we ask about a movie, we'll look for movies similar to that, ones that the similar users like.
Yeah. So this concept is.
This setup seems much more asymmetric. You haven't said there's movies and users with hidden things in between. You just said there's movies and hidden things.
Yeah, so the concept you are asking for, I think the machine learning term for it is collaborative filtering, where you take one user and try to find users similar and then try to find answers for them. So this actually, the RBMs can be used as building blocks in making these kind of things. I just wanted to pick the simplest setting where there are not too many layers of this, and so I just picked this. There are instances where you could like try to join a bunch of RBMs, or you could take two RBMs and then somehow do some other learning algorithm on top of the hidden side and things like this. Yeah, those are outside the focus of this talk, but it's a good question. So in machine learning, I think in general, people have used a lot of what are called linear methods, which just involve projecting to some subspace and then trying to figure out the eigenvalues and clustering based on that. And these days they use these kind of nonlinear models. I call it nonlinear because it's because there's an e to the power minus here that makes it nonlinear. And somehow these nonlinear models seem to work really well in practice. Another interesting nonlinear model is to emulate what our brain and neurons are doing. So they have some notion of an artificial neuron, and then it gets a bunch of inputs and applies a nonlinear function here. The function is actually just, it's something that looks like, yes, some activation, but it has a very nonlinear curve. And these kind of neurons are very useful in machine learning. For instance, the deep network that was used in playing Go uses these kind of artificial neurons a lot. So it uses these kind of neurons laid out in layers and then tries to optimize it. Again, we end up with optimization problems like this, where we have a parameter and we're trying to optimize some objective. So even though we are talking about specific models, there are a lot of salient features that are true in many other models. It is coming up. So again, in deep networks, at the end of the day, it's a low depth circuit. So what is known theoretically is that it's not going to solve any deep problem because it's only a low depth circuit. For instance, it can't even, if it's of depth 100, then it can't even understand a 101 parity function. So things like that. But then people, I mean, it anyway seems to work so well in practice that we should try to understand it. We should try to get more theoretical insights into it.